I will ask. Can anyone in the room let me know whether my screen is sharing? Yeah, I think that one's. Yeah, that one's good. Yeah, I think that one's good.
Right, we should start on the next keynote so that we don't too much delay, okay? Yeah. Okay, John.
Yeah, thank you for attending my today's talk. So today I will talk about an interesting phenomenon called mini bottlenecks and their impact on cloud application performance. Oh, okay. The enterprise computing infrastructure has been shifting from on-premises environment to cloud data centers. The main benefit is to reduce the infrastructure and management costs by sharing hardware resources. A recent study reports that 60% of enterprise applications are web applications. So there's a high demand to move web applications to the cloud. On the other hand, modern web applications typically have a strict response time requirement. For example, Amazon reported that every 100 milliseconds increase in page load decreases their sales by 1%. And Google also reported that a 500 millisecond additional delay in their search results could reduce their revenue by up to 20%. However, many cloud researchers and practitioners reported the long tail latency of their web applications when they deploy them in cloud, even they run their system at a relatively low utilization. So causing the performance unpredictability problem. Here's a quote from a recent issue of Communication of ACM that describes the challenges of the long tail latency faced by one IT company. Basically, their system encountered the inconsistent response time of their queries to the database. And every time they went to look for a root cause, the problem would disappear. So in today's talk, I'll show you one important reason for such mysterious long tail latency problems, mini bottlenecks. Mini bottlenecks are very short, are bottlenecks with very short lifespan, usually in terms of tens of milliseconds. For example, this figure shows a fine-grained CPU utilization of a web application server deployed in our data center and serve 9,000 users. The CPU utilization is measured at every 50 millisecond time window during a 20-second time period. We can see that the average CPU utilization is just 67% utilized. What's interesting here is that the CPU has transient saturations from time to time. And these transient CPU saturations create mini bottlenecks in the system. As we found out that even though mini bottlenecks are short-lived, they can cause large response time fluctuations for web applications, ranging from a few milliseconds to several seconds. This figure shows our measurement of the point in time response time of the web application during the same 20-second time period. The web application server, as I showed in the previous slides, is the most heavily utilized server in the system. So what this means is that the system has large response time fluctuations, even though the system is far from saturation. And in fact, our statistical analysis shows that over 2% of the requests take more than 2 seconds to finish. And such high percentage of long response time requests is considered as a severe violation of quality of service requirement by most e-commerce websites. So in this talk, I'll show you 2 case studies of mini bottlenecks that can cause a long tail latency problem. The first case study is mini bottlenecks caused by Java garbage collection. The second one is a mini bottlenecks caused by the interference of collocated virtual machines. In the second part, I want to choose how to exploit the mini bottlenecks to launch a novel type of DDoS attack. I'm going to start by describing our cluster environment. This figure shows a 4-tier topology of the web application that we use in our experiments. We use Apache as web server, Tomcat as application servers, and CJDBC as a load balancer for database, and MySQL as a database servers. We use Rubos, a well-known news benchmark website modeled after Slashdot. The workload generator of this benchmark simulates a number of normal users interacting with the web application. And the workload can be CPU intensive or mix of CPU and I/O. And in our experiments, we mainly focus on the browser-only CPU intensive workload. This figure shows a response time distribution of the benchmark website when it serves 9,000 users. The CPU of the bottleneck server in the system is just 61% utilized. And it is clear that there's a small portion of the request encountered long response time. So next, I'll show how the mini bottlenecks caused by the Java garbage connection in Tomcat leads to this long response time requests. This figure shows the Java garbage connection activities of the 2 Tomcat servers in our system during a 20-second time period. The x-axis is the time, y-axis is the Java garbage connection running ratio. So we can see that both Tomcat 1 and Tomcat 2 encountered frequent Java garbage connection activities. The figure on the bottom shows CPU utilization of the same 2 Tomcat servers during the same 20-second time period. We can see that once there's a Java garbage connection happens in Tomcat server, it corresponds to the transient CPU saturations of the same Tomcat. Okay, so this happens because Java garbage connection is a CPU intensive activity, and every time it happens, it will consume 100% of the CPU resources for 50 to 100 milliseconds. So this transient CPU saturations, as shown in the bottom figure, creates the mini bottlenecks in the system. The figure on the top shows the same CPU utilization of the 2 Tomcat servers from the previous slide. What we want to see is how these transient CPU saturations affect the queued requests in the system. The bottom figure shows the number of queued requests in both Tomcat and the upstream Apache. The pink line is Tomcat queue, and the blue line is Apache queue. So we can see that the transient CPU saturations in Tomcat match well with the peaks of the queued requests in both the Tomcat server and the upstream Apache. It's not a stretch to suggest that a mini bottleneck in Tomcat actually caused requests to queue in Tomcat itself. But why the same mini bottleneck can also cause even much larger queues in the upstream Apache? So I'll explain why this happens in the next few slides. The figure on the top, this figure shows the Apache queue from the previous slides. The figure on the bottom figure shows the point time response time of the system during the same 20-second time period. So we can see that the peaks of the Apache queue match well with the spikes of the system response time. Okay, suggesting that the spikes of the system response time are caused by the queued request in the Apache. So long queue in Apache also causes requests with very long response time in the system. The top figure still shows the Apache queue from the previous slide. The bottom figure shows the number of requests with response time longer than 3 seconds during the 20-second time period. So we can see that the peaks of the Apache queue match well with the happening of large number of requests with very long response time. So this happens because every Apache web server has a limited number of threads to process the concurrent request in the server. The underlying operating system also have a buffer size. The underlying operating system, TCP stack, also has a buffer for queued requests in the system. So the total number of requests that can be queued in Apache web server is the total number of threads in Apache web server itself plus the buffer size in the operating system, which is 278 in total in our case. Okay, once the queued request in Apache server exceeds the queue limit, the new coming request will be dropped, and TCP retransmission will happen. The current TCP retransmission protocol requires the client side to back off at least 3 seconds for the first time to resend the request. Due to the TCP transmission, then we observe a request with very long response time. Okay. So next, I'll explain why a mini bottleneck in Tomcat can also cause a large number of requests to queue in upstream Apache. Here is a simple illustration. At T1 time marker, requests start to queue in Tomcat due to a mini bottleneck there, and the Tomcat queue soon fills up, causing Tomcat to block new coming requests. At this moment, all the new requests are pushed back to the upstream Apache. Okay, so you can see that the bottom figure. So what's interesting here is that all kinds of requests start to queue in the upstream Apache. For example, the purple boxes, the requests for static images as shown by the purple boxes here. They are requests for static images. Okay, this kind of requests will never go to the downstream Tomcat, but because of the pushback of the requests from the downstream Tomcat to Apache, those requests for static images, they also need to queue in Apache. So this causes the queue amplification in the upstream Apache web server. Okay, so we call this phenomena as cross-tier queue amplification. Once the queued request in Apache exceeds the queue limit, the new coming request will be dropped. Okay, and the entire cross-tier queue amplification is very short. Okay, can happen within 100 milliseconds, but the performance impact is large. It can cause a lot of dropped requests. Okay. Oh. So in this set of experiments, I showed that mini bottleneck can cause large response time fluctuations, even though the system is far from saturation. Such large response time fluctuations are due to the cross-tier queue amplification, as I showed in the previous animation. In fact, the mini bottleneck caused by the Java garbage connection in this case can be easily fixed by upgrading the JDK version to a newer one. Okay, this is because a newer version JDK has more efficient garbage connectors. Okay, but there are mini bottlenecks that are not easy to fix. Okay, especially when the system is experience the bursty workload. Okay, so web applications are well known to have a bursty workload. For example, this figure shows a 5-second sample workload trace of a web application serving 8,000 users in our experiments. The request rate for this web application has significant fluctuations if monitored at every 50 millisecond time window. Okay, and we found out that the VM consolidation can cause hard to fix mini bottlenecks when it handles bursty workload. Consolidating VMs is a common practice for cloud vendors to increase hardware utilization and maximize profit. The state-of-the-art approach is to consolidate multiple underutilized virtual machines on the same machine using the classic beam packing algorithm. Okay? But there's a potential performance interference among VMs sharing the same hardware resources, especially for VMs hosting web applications. This is because web applications naturally have bursty workload, okay? And the sudden high resource demand of one VM can limit the available resource for the other collocated VMs, causing severe performance interference. Here we show our collocation strategy of two web applications in our cluster. The first system is called system steady. The second system is called system bursty. System bursty means that the users interacting with the web application are not independent. They're likely to send the request to the target system at the same time, and which creates a burst of request rate. Okay, and such bursty workload is very common in real world. For example, the traffic for an auction website like eBay, and many users tend to bid for the same item just right before the deadline. Okay, and based on the beam packing algorithm, okay, we collocate the system steady Tomcat with system bursty MySQL and collocate them on the same machine and let them share the same CPU cores. Okay, this is our topology of experiments, and the top figure shows the point in time request rate for system bursty during a 20-second time period. We can see that the frequent bursts of request rate for system bursty. Let's see how this burst of request rate affect the performance of the collocated system steady. Okay. The bottom figure shows a fine-grained CPU utilization of the system steady Tomcat. So we can see that the peaks of the request rate for system steady, for system bursty, match well with the transient CPU saturations of system steady Tomcat. This happens because of the performance interference of the collocated VMs. So the system steady Tomcat perceived transient CPU saturations because of the shortage of the shared CPU resources. Okay. And this transient CPU saturations in Tomcat creates mini bottlenecks in the system. Okay. So this figure shows the same CPU utilization of the system steady Tomcat from the previous slides. Let's see how these transient CPU saturations affect the queued requests in the system. Okay. The bottom figure shows the number of queued requests in both the Tomcat and the upstream Apache. We can see that the CPU saturation in Tomcat causes not only requests to queue in Tomcat itself, but also a lot of requests, a lot of queued requests in the upstream Apache. The long queue in Apache also causes requests with very long response time. Okay. The figure on the top still shows Apache queue from the previous slide, and the figure on the bottom shows the number of requests with response time, with very long response time. Okay, so we can see that the peaks of the queued requests in Apache match well with the happening of large number of long requests in the system. The reason is the same as what I have introduced in the first case study. The long queue in Apache causes new coming requests to drop, and leads to TCP transmissions and the requests with very long response time. Okay. So far, I have introduced two causes of mini bottlenecks in different system layers. the Java garbage collection in the system software layer, the VM consolidation in the application layer. In fact, there are many other factors that can cause mini bottlenecks in the system, such as the CPU power saving technology, the DVFS, or checkpointing to save state, or log flushing for monitoring systems. So regardless of these different sources, they can create short-lived mini bottlenecks. Okay, and even though these mini bottlenecks are very short-lived, they can cause large response time fluctuations for web applications. Okay. So now we have a better understanding of mini bottlenecks and their impact on end-tier web application performance. The second part of my today's talk is to extend the mini bottleneck research to the system security domain. Okay, the main idea is that can we purposely trigger the mini bottlenecks in the targeted system to create a new type of DDoS attack? Okay. So unlike the traditional brute force DDoS attack, our new attack is to degrade the performance of the target system, causing the long tail latency problem. For example, this figure shows the response time distribution of our 3-tier benchmark website under our attack. So instead of completely shutting down the targeted website, our attack is to make sure that the targeted website encountered the long tail latency problem as shown in this figure. Okay, so we call our attack as a tail attack because tail latency is what we want to achieve. The main idea of the attack scenario is to launch controlled bursts of HTTP requests in order to create a mini bottleneck in a target system. So this figure shows the on and off pulsating bursty style to launch our attack. So during the burst on period, the attacker sends a burst of legitimate but attacking HTTP requests to the target system. The purpose is to create a mini bottleneck in the target system. Okay, so by controlling the burst intensity and also the burst intervals, then the attacker is able to control the damage of the attack. For example, make the 95th percentile response time to be longer than 1 second. So here we show one reproducible tail attack scenario in our experiments. We still use a robust benchmark for illustration purpose. So we have two workload generators here. The first one is still the original robust workload generator, which is used to simulate the normal user behavior accessing the website. The second workload generator is used by the attacker, which is used to generate the burst of attacking HTTP requests. So this figure shows the concrete tail attack scenario. We choose a representative 8-second experiment period. The attacker sends a burst of legitimate HTTP requests every 2 seconds. So during the 8-second time period, we can see 4 bursts there. So this figure shows a fine-grained CPU utilization of each server in the system. So we can see that the burst of attacking HTTP requests actually cause transient CPU saturations in MySQL. Okay, and each saturation is less than 500 milliseconds. So this transient CPU saturations in MySQL creates mini bottlenecks in the system. This figure shows the queued requests in each tier of the 3-tier system during the 8-second time period. The pink line is a MySQL queue, and the blue line is Apache queue. So we can see that the mini bottleneck in MySQL not only cause request to queue in MySQL itself, but cause even much longer queues in the upstream Tomcat and Apache. Okay, and once the queued request in Apache exceeds the queue limit, the new coming request will be dropped and causing TCP transmissions. Of course, this the reason of this is because of the cross-tier queue amplification, as I introduced in the previous case studies. Okay? So this figure shows the evidence of the dropped request with very long response time. Okay, because the they encountered TCP transmissions. The happening of this dropped request match well with the peaks of the Apache queue, as I showed in the previous slide. Okay. So far, we can see that the tail attack is very harmful. Here, I want to show that tail attack is also very stealthy. Okay, these two figures show the CPU utilization of the three servers in the system, collected by monitor tools with different granularity. Okay, the top figure shows the CPU utilization of the three servers using 50 millisecond granularity. Okay, and we can clearly see the transient CPU saturations of MySQL. The second figure, the bottom one, okay, shows the same CPU utilization, but monitored at 1 second granularity. Okay. Unfortunately, we cannot observe any CPU saturation. Okay. Bad news is that majority of the mainstream monitor tools only support coarse-grained monitoring. They monitor in seconds or even minutes. Okay. For example, the Amazon CloudWatch by default only support 1 minute monitoring granularity. Of course, they can support finer grain monitoring, but you have to pay more. Okay, they charge you by turn on fine grain monitoring, and the finest monitoring granularity the Amazon CloudWatch support is 1 second. But even 1 second granularity is considered as a coarse grain in our scenario. So, which means that these coarse grain monitoring tools cannot detect mini bottlenecks in a targeted system. In other words, our tail attack can be stealthy to current detection and defense mechanisms. Okay. Now we have a general knowledge of the tail attack, but how can we actually launch an effective tail attack? So we have 3 knobs to control in our attack. Okay, the burst length, burst volume, and the burst interval. Okay, each burst is to create a mini bottleneck in the targeted system. Okay, and the length of the created mini bottleneck should be long enough to cause enough damage on the targeted system. On the other hand, the length should be short enough to escape the detection by the monitor tools of the target system. Okay. So to make an effective tail attack, we should solve 2 key challenges. First, how to infer the damage of an ongoing attack. Okay. Second, how to guarantee that our attack is stealthy. In other words, we need to be able to quantify these 2 metrics for an ongoing attack. Okay. To solve these 2 challenges, we use a customized queue network model to model the entire system under attack. The purpose is to fully understand the relationship between the attacking parameters and their impact on the attack damage and the mini bottleneck length. So once we fully understand the relationship between the attacking parameters and their impact, then we can apply feedback control to dynamically adjusting the attacking parameters to handle the various variations of runtime system conditions. Okay. Here is our queue network model for entire system. So for each tier, lambda is a request rate, and C is a service rate. Q is the capacity or queue size. So our queue network model is based on 2 assumptions. The first assumption is that the communication between every 2 tiers follows the RPC style call response communication. Okay, which means that when you send a request to downstream, you need a response back. Okay. And the second assumption is the queue in each tier is kind of limited. Okay. So under these 2 assumptions, then we know that every queued request in a downstream tier need to occupy another queue slot in every upstream tier. Okay. So as shown in this figure, this animation. So given the system model, we use a damage length to quantify the damage of a tail attack. Damage length is a period during which the new coming request will be dropped. Okay, as I explained before, once the frontmost tier queue is full, it will drop. New requests. Okay, so the damage length can be calculated by using the burst length minus the time to fill up all the queues in the system. Okay, so the burst length is controlled by the attacker. Okay, so in order to infer the damage length of our attack, we just need to know the time to fill up all the queues in the system. Okay, so given all the system parameters, we are able to derive the time when the queue of each tier is filled up. Okay, so the overall time to fill up all the queues in the system can be calculated. So I will skip those detailed explanations of the formulas. Okay, we can discuss more if you are interested. So in this case, so given the burst length and the time to fill up all the queues in the system, then we are able to calculate the damage length. So by controlling the damage length created by each burst and also the interval between bursts, the attacker can control the damage of the tail attack or cause on the target system. Okay, so for example, making the 95 percentile response time to be longer than 1 second. So the second metric is Millibottleneck length. This metric is to quantify the stealthiness of a tail attack. Millibottleneck length is determined by two parts. The first part is the total processing time of the attacking request within one burst. The second part is the processing time of normal requests during the same burst period. Okay, so both two parts can be derived from our attack model. Okay. So I'll skip the detailed explanations of the formulas. So given the damage length and the Millibottleneck length derived from our attack model, an attacker is able to control the damage and the stealthiness of the attack by tuning the attacking parameters. Okay, so we implement a self-adaptive attacking framework. It can dynamically choose the optimal attacking parameter. To meet attacker's goal. For example, a 95 percentile response time to be longer than 1 second, and also the created Millibottleneck length to be less than 500 milliseconds. Okay, so the framework itself includes the two parts. One is the estimator, the other is the controller. The estimator uses a prober to estimate the damage length and the Millibottleneck length created by each burst. Okay, and then the controller takes these two estimated metrics and then adjusts the attacking parameters in order to fit the dynamics of the system conditions. For example, the variations of background workload. Okay, so in this case, the attacker can always achieve the attacking goal regardless of the variations of the background workload. We know that the web application, the workload can change during the days or even during a short time can also change. So there are many challenges to reliably detect and defend the tail attacks. The first challenge is how to reliably detect Millibottlenecks in the target system. Okay, this is because Millibottlenecks are short-lived. Many existing tools either do not support fine-grained monitoring or they cause high overhead for fine-grained monitoring. Okay, in addition, many potential resources can cause Millibottlenecks. Okay, those resources may be beyond the coverage of typical monitoring tools, so they cannot the tools cannot detect the mini bottlenecks. Okay. The second challenge is that how to distinguish the mini bottlenecks caused by the legitimate workload and the attacker itself. Okay, this is because the workload for web applications is naturally bursty. So the normal detection tools are likely to cause like high false positive and high false negatives. Okay, so all these challenges. Okay, all these challenges can make the detecting and defending our tail attack a kind of open research question. Okay. Someone may ask, why are mini bottlenecks not a problem before? Okay. One important reason is that the impact of mini bottlenecks highly depends on the types of the workload. For example, the batch workload used in data warehousing are usually throughput oriented. They are not latency sensitive. Okay. The traditional queue network, they assumes stable workload composed of independent jobs, which cannot generate a cross-tier queue amplification. Okay, if you have such a independent job assumption, and the MapReduce Hadoop workload. Okay, they are embarrassingly parallel. The lack of strong interdependencies among servers. Okay, they also cannot generate the cross-tier queue amplification in such type of workload. On the other hand, the N-tier web applications in general are latency sensitive. They naturally have bursty workload, and unfortunately, they also have strong inter-component dependencies in the system. So all these features of web applications make mini bottleneck having a bigger impact on this type of workload. Okay. So the second reason why mini bottlenecks are new is because of the monitoring granularity of typical monitoring tools. Okay, they in general support seconds or even minutes level monitoring granularity. So mini bottlenecks are kind of invisible for them. The third reason is adoption of cloud computing. Okay, data centers or cloud computing environment are supposed to run at high utilization for high return on investment. But a recent Gartner report shows that the servers in typical data centers are only busy 18% on average, wasting a lot of resources and power. Okay, our research shows that mini bottlenecks are an important factor to this resource utilization paradox. For example, web applications can encounter unpredictable performance even at a relatively low utilization. Okay. So but if we can understand the mini bottlenecks better, we can manage them better. Our final goal is to increase the resource utilization and also maintain the high performance of the targeted web applications. Okay, so there are many interesting open questions and the future one. For example, what other factors can cause mini bottlenecks in a cloud, and how to effectively detect these mini bottlenecks? The second question is that what is the impact of mini bottlenecks on other type of latency sensitive cloud applications? I listed two application domains here. One is microservices, the other is real-time stream processing. Okay, microservices in general has a much more complex inter-service dependencies than the traditional N-tier architecture. So we believe that mini bottlenecks has even bigger performance impact on this type of microservice applications. The second application domain, the real-time stream processing. This is because real-time stream processing, their target usually or their users are usually machines. Okay, and machines usually are more latency sensitive. Okay, for example, many cars. Okay, they generate messages to be processed by the stream processing system, and the car wants much faster response time from the system. Okay, they are more sensitive to latencies. So we believe that the mini bottlenecks also have big impact on this type of application, on this type of applications. Okay. So the third open question is that can we predict a safe utilization boundary for cloud applications? In this case, we can solve or at least mitigate the resource utilization paradox in current cloud data centers. Okay, and we are able. In this case, we can achieve higher utilization of the cloud resources and at the same time avoid the unpredictable performance problems. Okay. Yeah, that's my today's talk. Any questions?
Well, one of the points you mentioned, like on Java 1.8, the garbage collection was fixed. Like fixed this the problem. You mentioned that the garbage collection usually as a resource consuming process that take 100% of CPU. Can you explain a little bit more how the Java 1.8 fixed that problem?
There are different Java garbage connectors. Okay, the first old one, they use kind of stop the word serious Java garbage connector. Once it do garbage connection, it will kind of stop processing the normal request in the system. The newer version garbage connector, they support like a parallel garbage connector or even a concurrent garbage connector. They can do the garbage connection at the same time process the request in the system. Okay, they kind of cause mini pauses in the system instead of the stop the word garbage connector. Okay, so in this case, their impact on the application is much smaller than before. But very good point. In fact, when I say that the newer version of garbage connector fix the problem, in fact, it's just fix the problem in our case. It doesn't fix the problem in large scale web applications. In fact, our experiments, for example, I mentioned about the real-time stream processing, and our the Java heap size can reach to like 40 gigabyte or even 100 gigabyte, and Java garbage connection still has big impact on application performance. I just didn't cover it here. Okay, so garbage connection is very complex, and yeah, still ongoing research there.
Any other questions? Yeah, actually, Dr. Wang, I have one